What if the future of deep space travel didn't rely on massive fiery explosions, but rather on a silent blue beam of ions or the raw power of the atom? Welcome to this explainer. Today, we're cutting through the sci-fi hype and confronting the absolutely massive engineering hurdles standing between humanity and the red planet. Because getting boots on Mars, and actually keeping those boots alive, requires us to completely rewrite our deep space playbook. Now, you and I are totally used to watching these enormous, explosive chemical rockets lift off from the pad. It's iconic. But deep space travel demands a totally radical rethink of physics. We really have to ask ourselves, could a propulsion system firing a silent, continuous beam of ions or a superheated nuclear reactor actually be our only real ticket to Mars? Let's get right into it with Part 1, the Mars propulsion problem. To really grasp why we need these exotic engines in the first place, we have to look at the sheer, mind-boggling distance to Mars and the harsh limits of the technology we're flying right now. Look, conventional chemical rockets, like the ones that powered Apollo or our current Artemis missions, they're incredible machines, no doubt about it, but they rely on combusting heavy propellants. And because the exhaust byproducts of that combustion are relatively heavy, you are fundamentally limited in how fast you can push your spacecraft. You want to go faster? Well, you're going to need more fuel, but that makes the ship heavier, which means you need even more fuel just to push the fuel you just added. It's a massive, incredibly inefficient bottleneck. Moving on to Part 2, the saviors, nuclear thermal versus nuclear electric. So, how exactly do we break that chemical bottleneck? Well, the two primary solutions both rely on splitting the atom, but they do it in completely different ways. First up is nuclear thermal propulsion, or NTP. You can think of this as the sports car approach to space travel. Instead of burning a mix of chemicals, an NTP system pumps super cold liquid hydrogen directly through a nuclear fission reactor. The reactor rapidly heats that hydrogen up, expanding it into a high-pressure gas that absolutely blasts out the nozzle. This gives you high thrust and roughly double the efficiency of your standard chemical rocket. But then we have nuclear electric propulsion, or NEP. This is the ultra-efficient hybrid approach, and this is where those ion engines come in. In this setup, the reactor acts like a flying power plant, generating massive amounts of electricity. That electricity is used to ionize an inert gas, usually xenon. Then, an electromagnetic field accelerates those ions out the back of the engine. There's no massive explosion. Instead, it creates a silent, continuous, gentle nudge. And over months of deep space travel, that gentle nudge builds up to absolutely incredible speeds. It really all boils down to a battle of thrust versus efficiency. In rocketry, we measure that efficiency as specific impulse, or ISP. With NTP, you're getting high thrust to cut your travel time using brute force, giving you an ISP of about 900 seconds. NEP, on the other hand, gives you very low thrust, but it leverages an extremely high exhaust velocity. We're talking an astonishing ISP of 2,600 seconds or more. It sips its fuel incredibly efficiently. And here is the literal mass cost of that efficiency, which is absolutely wild when you look at the numbers. If you use a standard chemical rocket for a Mars mission, a measly 3.4% of your starting mass is actual useful payload. Everything else? Just fuel and the tanks to hold it. But look at the nuclear options. Even when you factor in the ridiculously heavy weight of a fission reactor and all its radiation shielding, nuclear electric bumps that useful payload fraction up to almost 10%. And nuclear thermal? That pushes it over 12%. To put that into perspective, that means substantially more cargo, bigger habitats, and way more supplies actually making it to the Martian surface.
All right, Part 3, the reality check. Project Draco's downfall.
Okay, so the physics sound incredibly promising, right? But we have to look at the devastating real-world complications here. And honestly, nothing highlights this better than Project Draco. DARPA kicked this off in 2021 with the goal of actually testing a nuclear thermal rocket in space by 2027. By 2023, NASA had jumped on board. It was the most momentum we had seen for space nuclear propulsion in decades. And then, poof, in 2025, the program was just abruptly canceled. So what happened? Why did it fail? Well, it wasn't the physics that killed Draco, it was the economics. You see, massive reusable chemical rockets, like SpaceX's Starship, have caused the cost of a launch to absolutely plummet. With it becoming so incredibly cheap to just launch heavy chemical fuel into orbit, the billions of dollars required to research and build a nuclear engine suddenly lost its return on investment. Add to that the absolute regulatory nightmare of trying to ground test a nuclear reactor that exhausts irradiated gas on Earth. Plus the headache of storing liquid hydrogen at cryogenic temperatures for months on end, the costs simply outgrew the benefits. Let's head into part 4, deep space radiation threats. Because let's say we do overcome the propulsion problem, we still face a second massive hurdle. Deep space is actively trying to kill the crew before they even get there. The primary villain in this story? Galactic cosmic rays, or GCRs. These are highly energetic radiation particles blasting in from outside our solar system. If you take a long transit time in a slow chemical rocket, you risk pushing your astronauts past NASA's strict career radiation limits in just a single mission. We're talking a drastically increased risk of cancer and severe cognitive decline. Now, here's a fascinating and honestly pretty counterintuitive question for you. We know the sun is also blasting out radiation, right? Especially during periods of violent, high solar activity that we call a solar maximum. So why on Earth would mission planners actually want to send astronauts to Mars when the sun is at its absolute most aggressive? It's a phenomenon known as the solar maximum paradox. See, while the sun is indeed throwing off more solar radiation, that intense activity actually strengthens the heliosphere. That's the massive magnetic shield stretching across our entire solar system. This beefed-up solar shield literally blows away those much deadlier galactic cosmic rays coming from deep space. Surprisingly, launching right in the middle of a solar maximum can actually reduce a crew's cosmic ray exposure by up to 70%. Crazy, right? Which brings us to Part 5, Shielding the Mars Crew. Of course, we can't just rely on the sun's schedule to keep us safe. We need physical shielding for the ship and the surface habitats once we land. Now, you might be thinking, okay, just build the spacecraft with thicker metal walls, right? But space physics plays a really cruel trick on us here. Why does adding more standard aluminum shielding actually increase an astronaut's radiation exposure on Mars? The answer comes down to something called secondary neutrons. When a high-energy cosmic ray strikes a dense metal like aluminum, it doesn't just stop. It shatters the atoms inside the metal, creating a massive shower of highly penetrating secondary particles. Think of it like a cue ball smashing into a tight rack of pool balls. By surrounding your astronauts with thick aluminum, you are essentially just providing more targets for the cosmic rays to hit, which creates a deadly radiation shower right inside the habitat. So the solution here isn't heavy metal, it's hydrogen. Hydrogen is uniquely suited to absorb these secondary neutrons, while aluminum creates that deadly secondary radiation. A material like polyethylene, which is basically a super hydrogen-rich plastic, effectively absorbs it. Packing the inner walls of the spacecraft and the surface habitats with a plastic like polyethylene is quite literally the ultimate lifesaver for a Mars crew. To summarize everything we've unpacked in this explainer, there's a quote from Stanford's Mars Transportation Study that really hits the nail on the head. They note that while nuclear propulsion can increase payload fractions, the added system complexity can completely eat up that mass advantage. Both NEP and NTP require targeted, sustained development to actually be credible. Basically, the physics for an efficient Mars transit using nuclear engines absolutely work. But the engineering complexities, the massive regulatory hurdles, and the realities of radiation shielding demand serious commitment. It is never as simple as just building a better rocket. Which leaves us with one final lingering thought. As the cost of hauling chemical fuel into orbit continues to drop, will humanity actually take the massive financial and engineering leap to invest in fission reactors and silent blue beams of ions? Or will our dreams of truly exploring the deeper solar system remain forever bound by the limits of chemistry?